Okay, welcome to a lecture here. All right, so we're going to sort of continue on and continue to kind of go through some of the chapters here and some of the topics that we talked about this semester. Then we'll kind of knock off like normal and take a little break. And then obviously we will have our exam during lab time. And we'll take it like normal there, again, with your camera on in the Zoom meeting and all that good stuff. All right. So we last left off, I think, got through sort of, let's say, chapter 14. And chapter 14, again, was sort of the acid-base chapter, where we talked about, obviously, acid bases. We talked about pH. We talked about H plus, OH minus, the pH scale. We also talked about weak acids and weak base type equilibrium. And we also dealt with salts, which was an important part of that chapter. Again, salts that go through hydrolysis and will either produce H plus or OH minus and make that solution really either acidic or basic, depending on sort of what it produces. There are certain salts, right, as we talked about, that are neutral salts. Again, they come from a strong acid or a strong base. And again, that's the relationship there that they will have opposite sort of relationships with their conjugate acid and conjugate base pairs. So something comes from something that is strong, it is a relatively weak conjugate acid or conjugate base. Well, again, if something is on the weak side in terms of acid or base, it will basically have a partner that is relatively strong if it comes from something that's weak. So at that point, we've now gone to, I think here, chapter 15. And in chapter 15, we talked about some really big type topics, and that's basically buffers and titrations. So we started off sort of talking about in chapter 15, the idea of the common ion effect. And the common ion effect, as the name implies, and as we talked about, will have an effect on the ionization of a weak acid. It basically will suppress the ionization of a weak acid or base. And it's a basic sort of Le Chatelier's principle. So, for example, we looked at acetic acid, which under normal conditions here will break apart obviously into H plus and acetate. And as we talked about, which I think was also the example here, if we had the acetic acid not in just a solution by itself and sort of water, if you will, but if we put it in maybe a solution that contained sodium acetate, because sodium acetate again is a salt, it will 100% break apart into sodium and basically acetate. And when we do put this guy into a solution like that, that is essentially like adding more acetate, which is our common ion. And Le Chatelier's principle will say it will shift to the left in this case. And because, again, it's shifting to the left, what that's going to do in the case of our weak acid or our weak base is basically keep it together. It's not going to allow it to release as much, in this case, H plus as it normally would. And we would see in terms of effect on certain things like pH, we would expect the pH of this solution to be relatively higher than the pH of, say, the acetic acid by itself, again, because of that Le Chatelier's principle, where it's basically pushing the whole thing kind of back together and keeping it together rather than letting it basically dissociate and break apart. Sort of a big idea that is pretty much a common ion effect is the idea of buffers. And buffers are pretty much that deal, your common ion. And buffers are solutions that basically contain a combination of either a weak acid and the salt of its conjugate base, or you could have a buffer that contains a weak base and the salt of its conjugate acid. And remember that when you have a buffer, basically both of those things are in the buffered solution to begin with. And that's why they're really able to work and do what they do, which is they're able to maintain their pH even when acid or base is added to them. And remember that, as we talked about, again, a buffer is not a neutral solution with something with a pH of 7. It just means that whatever pH it starts at, it's able to, again, maintain that pH even when you add acid or base to it. So if you had a buffer at a pH of 9, it should basically maintain that 9, even if you add acid or base to it. As we also talked about, if you were following it with something like a pH meter, you would actually see the pH go up and down a little bit, but we wouldn't see a tremendous jump in the pH one way or the other when we add either acid or base to it. And it's able really to maintain the pH because it's ultimately able to keep the H plus concentration relatively constant. And the way it does that is simply, as we sort of talked about a number of times, if we take HCl just by itself and dump it in water, which is not a buffer, it is going to produce H plus and Cl minus. And it's going to produce a lot of H plus really quickly, which we would expect a pretty good jump in the pH at that point, because the more H plus you add, the more effect it has on the pH of the solution. If we take that same HCl like we talked about and put it into a acetic acid sodium acetate buffer, for example, it would react with the sodium acetate, which is the base part of the buffer, and it would end up making acetic acid and a little sodium chloride. And what we also saw was it will typically make the other part of a buffer. So as you sort of use a buffer, one part goes down, the other part goes up. And the most important thing, as we see here and we talked about, is we really, when we have a buffer, prevents the formation of free H plus or free OH minus in the case of adding a base to it. And that's really important because really the H plus concentration and the OH minus concentration, as we talked about last time, are inversely related to each other. So as one goes up, the other goes down, which means in this situation, when we add the acid to the buffer, we do not produce any more free H plus, which again means that the relative concentration of H plus remains the same, and thus the pH will not jump very high or not. You will actually, again, see a little bit of that. And that is sort of what we talked about when we sort of drew this sort of picture. Typically speaking, when we do make a buffer, again, there's the acid part, there's the base part of our buffer. And when we add acid to it, what happens is we end up making more of the acid part of the buffer, and we end up using some of the base part of the buffer in that reaction. And same thing happens when we add base to it. Again, when we add base, it's going to react with the acid part of the buffer and actually make more of the base part of the buffer. And this is also what we talked about in terms of the idea of buffer capacity. So buffer capacity, again, is that idea that, there is a limit to how effective a buffer could be. And in this case, for example, if you look at either of those sides, if you just continue to add acid, like say over here, eventually you will just continue to eat up the base part of the buffer till there's really kind of no base part left. And at that point, it no longer has the ability to prevent the free H pluses from forming. And at that point, you would see a pretty big jump in the pH because you kind of blew by it, and the base part of the buffer basically got used up completely. This could happen a couple different ways, as we sort of talked about throughout the semester here, but remember that when you do make a buffer, there's only really a certain amount of moles of the acid part and a certain amount of moles of the base part that's really available to react. So if you, for example, as we talked about, maybe went to the shelf and grabbed the wrong acid off of there, a really concentrated amount, and dumped a whole bunch of it in there, all that moles of acid you just put in is going to be way too many moles for our buffer to handle. And again, we'll use up all of the base part of the buffer, and you would see a tremendous sort of jump in pH. And when we talk about these buffers, obviously we need to do some calculations, and there was the Henderson-Hasselbalch equation that we typically do use for buffers. And the pH is equal to the pKa plus the log of the base over the acid. And in this particular case here, as we've talked about, the pKa value is minus the log of the Ka value. So that, again, is how you calculate the pKa value. And here we use the base over the acid. So this is a way that you can calculate the pH of a buffer. And if it is just the buffer by itself, you haven't added anything to it, you could just directly go into that equation, obviously, and calculate it. You could also do an ice table like we talked about. So for example, if you had the acetic acid buffer, you could still, if you prefer, do an ice table, and it would just be your dissociation of your weak acid. You could use your Ka value in this ice table. But the important part of this ice table is, if it's a buffer, is that you do need to have numbers on both sides, which is a common mistake people make when they sort of use an ice table instead of sort of the Henderson-Hasselbalch equation. So perfectly fine to do the ice table like we talked about, and we sort of did it both ways as well. But again, that's where most people make a mistake, especially if it's a buffer. They don't have that initial concentration of, in this particular case, the conjugate base. Now, we also saw as well that this Henderson-Hasselbalch equation is useful for really any type of buffer. You could use it for an acidic buffer, a basic buffer, neutral buffer. It doesn't really matter. But sometimes people will use sort of the POH version of it, which is the pKb plus the log of the acid over the base. So some slight differences here. And as we talked about, the pKb would be minus the log of the Kb value. So as we talked about as well, you know, you could use this, it's perfectly fine if you choose to use it. But again, in most cases, what you're asked to solve for is the pH. So as we talked about, you then still have to subtract 14 from it to get to the right pH. Again, in most cases, you can just go directly into here, as long as you have the pKa value and so forth, and actually calculate the pH directly, which is typically what you're usually asked to calculate. And there's that nice relationship as well. If you take the pKa plus the pKb, it does equal 14. So that's a good little relationship as well. So we could use the Henderson-Hasselbalch here equation specifically for buffers. That's really what that equation is for. And the other thing that people need to watch out for, as we talked about many times, is, again, we don't want to overuse the Henderson-Hasselbalch equation in situations where it is not a buffer. So you wouldn't want to use that if it was obviously not a buffer situation. Now, we also talked about in relationship to buffers that you can figure out what happens when you do add an acid or base to it. And remember, this was sort of our first situation where we have to take into account, when we do an ice table, the idea of adding volume. And when we add volume, it's really important when you do your ice table to make sure that you do it in moles. So again, this would be a situation where you want to do that table in moles. Because it is a buffer, it would be the moles of sodium hydroxide in this case that would add. And again, if it is a buffer, also important to have that initial concentration here, our initial moles here. And again, after you do this ice table, as we talked about in moles, you'll be left with moles of this guy, moles of this guy. And again, at this point, you are left with a buffer still when you do this sort of addition, but very important to do that first table in moles. Usually also really good practice to convert it back to molarity there using the total volume at that point. And again, at this point, you do have two options in terms of the pH. You could ice table it, or again, as we talked about many times, probably just as easy and probably good move to go directly back into that Henderson-Hasselbalch equation. Now, as we also talked about, I think as well, if you do this sort of first ice table in moles and you're left with a buffer at the end, you can go into the Henderson-Hasselbalch equation. If you use the Henderson-Hasselbalch equation with moles of your base and your acid, it will work out the same. So you could either go with moles or molarity. But as we did mention, it's probably a good idea to convert it back to molarity, usually after that first table, because there's a lot of calculations where you do need the molarity to kind of continue on with the calculation. So it just sort of works out a little bit easier there. So usually you got to do that first table in moles, usually good practice. After that first table in moles, we then convert back to molarity and then kind of continue on with our calculation. Let's see, that was buffers. In addition to buffers in that chapter, we had our favorite stuff, which was titrations. So remember that titrations is typically when we add a solution of known concentration to an unknown concentration solution. And usually we titrate right until we reach what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where the moles of the acid equals the moles of the base. Usually we use an indicator, right, to help us decide when we should stop our titration, which is sometimes referred to as the end point of the titration. And in a good titration, your end point and your equivalence point should really be the same or very close to each other. And when we talk about an indicator, right, we talked about choosing a proper indicator, and indicators essentially work over a pH range. And what you're looking for is really usually a change in color, a sort of visual change in color that you could actually see somewhere near where you expect the equivalence point of your titration to occur. So how do you know where you expect your equivalence point to kind of occur? It does depend on the type of titration that you're doing. And we talked about really three types of titrations. We talked about the titration of a strong acid and strong base titration. You know, so this would be something like HCl and sodium hydroxide. And we also looked at titration curves, right? And in this case, volume of base and pH. And in a titration curve, we have something that looks something like this, sort of. And we have this usual S sort of shape. And again, there's really, when you think about titrations, as we talked about, sort of four different areas on there. You know, there's the start of the titration before you begin, sort of area one. And really in this type of titration, before we begin, the only thing you have is a strong acid, which means because it's a strong acid, it's going to 100% break apart, which means that you could just go directly into the pH equation because you do have the H plus concentration given to you. So before you start the titration, to find the pH of that solution is pretty simple, just directly into there. Then as we sort of titrate, we are going to be pretty much doing a reaction that's going to occur here. And this reaction that's going to occur is going to require you to do one ice table. So you do have to do an ice table here. And it does have to be in moles because you are adding. And really the only purpose of this ice table is when you do this reaction, because at this point in the titration, for example, for adding the sodium hydroxide in the burette to the HCl that's in the flask, the HCl is the excess reagent. The sodium hydroxide at this point is the limiting reagent. So the purpose of that ice table is to figure out the concentration of your strong acid at the end. And that means that you do it in moles. You then would convert the moles to molarity using the liters, and that gives you your concentration. And then you could go into the pH equals minus the log of the H plus at that point to get the pH. Now, once we do reach the equivalence point here, again, that's the point where the moles of the acid equals the moles of the base. And at that point, that means that pretty much all of the HCl would be gone in our example here. All of the sodium hydroxide would be gone. And exactly at this point, we're left with water and sodium chloride, which is a salt. So we're left with a salt like sodium chloride. And again, this salt comes from a strong acid and strong base, which means it is a neutral salt. And that means that at the equivalence point in this type of titration, we would expect the pH to be neutral or 7. And again, this is how you would know if you're doing a strong acid, strong base titration, that perhaps you need an indicator that will change color around a pH of 7 to tell you to visually sort of stop your titration. Obviously, once we hit the equivalence point and we kind of just keep going and shoot way past it, and sort of our fourth step there. And in step number 4 here, we're definitely past the equivalence point. So essentially, as we talked about, you're essentially just dumping base in at this point. And since you are past the equivalence point, you basically have now changed what's happening here. The sodium hydroxide in this example now becomes the excess reagent, and the HCl becomes the limiting reagent, which means actually the amount of HCl will get used up. So this requires an ice table, also done in moles. And again, the purpose of this table is actually to figure out the concentration of your strong base that's left over. And again, you would convert those moles into molarity using the total volume in liters. And at this point, that would then give you the OH minus concentration because it's a strong base. You then could get the POH and then get to the pH because of that. So that was that first type of titration that we talked about. Now, we also talked about another type of titration. And again, it's kind of a similar setup. We're going to have the base up in the burette, the acid down in the flask or the beaker. So this would be a titration of a weak acid, again in the beaker or flask, and a strong base up in the burette. So like the one we talked about, something like acetic acid plus some sodium hydroxide, again going to make a little sodium acetate and some water in this particular case. So we also had a titration curve that we sort of looked at here. Again, pH would go here, our volume of base that we're adding here, going to give us that fairly badly drawn curve. Let me try that again. Take 2. Let's go this way. Let's go that way. Let's go. That's even worse, but we'll use it. Pretend it's sort of straight. That's a really bad curve. All right, so we got this, semi-bad curve here. And we have really, in this case, sort of the same 4 areas that we usually focus on in this type of titration. Again, right here, before we start the titration, this one is a little different than the previous one because what we have in the flask here is not a strong acid, it's actually a weak acid. And because it's a weak acid, it requires you to do an ice table. And this would be with molarity and X's. And you would solve for X. And X would equal the H plus concentration, which then you could go and calculate the pH from. So a little bit different than the previous one. It's a little bit more work on this one at the beginning of the titration here. You do need to do an ice table with molarity. Again, you can use molarity because you haven't added anything yet. And then once you figure out what X is, that should be your H plus concentration. And then you could go into your pH equation at that point. Now, once we start this titration here and we start to head towards the equivalence point, I'll just make my bad equivalence point there. So anywhere from before the equivalence point to where we start sort of our titration here, we are going to have a similar thing as the previous one. You need to do an ice table for that reaction because we're now adding, it does need to be done in moles. And the whole purpose of this area here is, if you remember, what you will end up with is a buffer. So the purpose of this is you're going to end up with the concentration of your weak acid and the concentration of your conjugate base, which means you need to do that one ice table in moles, convert it back to molarity, and then at that point, because you will always have a buffer that is there, you could go right into your Henderson-Hasselbalch equation. Or again, you could do a second ice table and skip the Henderson-Hasselbalch equation if you choose to do so. So you're always going to end up with really an acidic buffer in this region as you go through the titration. When we get to the equivalence point here in this type of titration, at this point, again, we're going to use up all of our acid we started with. We're going to use up all of our bases. And the only thing that we will have left over again at this point is a salt. And in my example up here, something like sodium acetate. Now, the deal with this salt is part of the salt comes from a weak acid. And because part of the salt comes from a weak acid, it will go through hydrolysis. And it will react with water, part of that salt. And because it comes from a weak acid, it's going to act as a base, which means it will accept an H plus from water. And when it accepts an H plus from water, we're going to produce OH minus. And because we're going to produce OH minus, we should know that the equivalence point in this type of titration should be basic. So here we would want to choose an indicator where we would see a color change in the basic region rather than maybe something in the acidic region or anything like that. What this means in terms of calculation is it usually requires 2 ice tables at this point. First table is done in moles, and the purpose of that is to get the concentration of the salt. The second one is your hydrolysis ice table, where the salt reacts with water to produce hydroxide. And also very important in this case is you most likely have the Ka value, you need the Kb value. You're going to solve for X. X is going to equal the OH minus concentration, which means you get the POH and then you get to the pH at that point. Obviously, the second ice table here would be done in concentration, molarity, and also X's. And you again solve for X and it'll get you there. Then we talked about after the equivalence point, same situation is going to occur. You again are going to be just dumping in excess sodium hydroxide in this particular example, or excess strong base. And that means you're going to get a buildup really of strong base. And same thing is going to happen. Our acid here will become the limiting reagent, while the sodium hydroxide will become sort of the excess reagent. So you do need to do one ice table, also in moles, and then convert to molarity to figure out the concentration of your strong base. Because at this point in the titration, you will have the strong base there, and you will also still have this salt there that's present. And between the two, the salt is a base, and the strong base is obviously a base. But out of the two of them, the strong base, like sodium hydroxide, will be the major contributor of OH in that solution, which means you essentially then will have the OH minus. You then can go to your POH and then to your pH, right? And again, you can see here really the same sort of 4 areas on the titration curve, but some different ways that you need to solve these because of the type of titration it is. And again, that's why it's really important to understand, as we talked about, sort of where you are in the titration and what type of titration you're talking about here as well. The other important thing as well, as we talked about when we looked at sort of this titration curve, is as bad as I drew it here, when we do approach the equivalence point, I'll just kind of draw it right here, kind of straight up, we do end up going relatively vertical to the equivalence point. And that's what we see in most titration curves is, you know, in this case, we have sort of that buffer region. And at some point, you typically will see a pretty good jump in pH to the equivalence point, and then you will see a jump past the equivalence point in terms of pH. And as we talked about, this is why when people have done titrations before, maybe yourself included, it's very common to hear, I don't understand, like the indicator went super pink. Again, I only added 1 drop. And you can see here from this really badly drawn curve that just adding a little bit of volume in certain areas of the titration is enough to make a pretty good jump in the pH. And since indicators work over a pH range, that's a good place to see a pretty good jump in the color that you see in terms of the indicator and what's happening. And also why that if you kind of miss the equivalence point by a drop or 2 and it even went super dark, it's really not that critical in calculations as long as you didn't like open it up and just let it flow in there nonstop and really just jump way past the equivalence point. So that's this type of titration here. And then we finished up talking about a third type of titration, which is a strong acid weak base titration. So a strong acid weak base titration. And again, in this case, a little bit different. In this case, actually the base is in the beaker and the acid is up there in the burette. So we're actually adding acid to the base. And so something like, I think this is the one we looked at, where we use ammonia, which is a weak base. Hydrochloric acid, obviously a strong acid, going to give us something like ammonium chloride. And again, in this titration curve, we actually have the volume of the acid being added and the pH. And this curve's a little bit different, but very similar to the second curve. It just sort of goes the opposite way. It's sort of dumped upside down. And that is because, again, in this case, the base is actually in the beaker to begin with, and we're adding the acid to it. So when we start this titration here, we have a similar type of thing like the last one, except that we're starting with a weak base. So this is really just a KB problem with a weak base. Again, you could do an ice table in molarity because you haven't added any acid in this case. You're going to solve for X. X is going to equal your OH minus concentration in this case, going to get you to your POH and then to your pH. So again, requiring that one ice table and to get to your concentration of your weak base. Again, our equivalence point we'll just put here. Before the equivalence point to starting the titration, that's area number 2. And in this case, if you remember as well, we actually do end up with a buffer in this region as well. And that's because when it's all said and done, we will have our weak base left over and our conjugate acid there, which requires you to do an ice table in moles. And once you do, you can convert it back to molarity, which will give you the concentration of your weak base and your conjugate acid. And again, that is really a buffer in this particular case. And in this case, we will end up with a basic buffer, which means you could still use the Henderson-Hasselbalch equation, even though it's basic. Or just like we talked about previously, you could also have done a second ice table and forget about the Henderson-Hasselbalch equation at that point. Now, when we do reach the equivalence point, you again used up all your acid and all your base, and you are left with a salt. And this salt did come from a weak base, which means it will go through hydrolysis. The difference, though, is when it goes through hydrolysis, because it came from a weak base, it's going to act as an acid, which means that acid is going to donate the H plus to the water, and you're basically going to produce H3O plus, which means we would expect at the equivalence point here for it to be acidic, which in terms of our indicator here, again, we would want to choose an indicator that basically will change color in the acidic range, as that would be most helpful to us. In addition, just like the last one here at the equivalence point, does require 2 ice tables. First one, again, in moles, and then really converted back to molarity. And just like the last one, the purpose of that first table is to figure out what the concentration of the salt is. And then the second ice table is your hydrolysis one. And again, here you probably have a Kb value given to you. You need to use that Kw expression to convert it to Ka, and that will give you your H plus concentration, and then you could go into your pH once you solve for X. So very similar to the titration we were just talking about, just sort of backwards. And obviously once you pass the equivalence point, here, because you're adding acid, you're essentially just dumping a whole bunch of acid in there. And it does require a ice table done in moles and then converted to molarity. And the purpose here is to get the concentration of your strong acid that you're dumping in there, which will give you your H plus concentration, and obviously will directly give you your pH in this particular case. So extremely important to understand where you are in the titration, as we talked about. Again, it's really good to have in your head what type of calculation you should be doing, because if you know where you are, you can basically figure out, you know, the type of calculation you should be doing in those particular cases. A couple other things we talked about in terms of figuring out some certain things. You could figure out the volume to reach the equivalence point. If it's a 1-to-1 relationship in terms of the stoichiometry of the acid and base, you could do M1V1 equals M2V2. If it is not a 1-to-1 relationship, you do have to take the stoichiometry into account when you're trying to figure that out. So you could do a basic stoichiometry problem. And if you have the same concentration of acid and base, and it's a 1-to-1 relationship, whatever you started with in terms of the volume of the base, for example, is how much acid you would have to add, or vice versa, again, in that situation. All right. That was, I think, chapter 15. Any questions on titrations, buffers, any of those fun stuff there? All right, then we rolled into chapter 16, I think. And chapter 16 dealt with some more equilibrium, some KSP, and we came back to KF, which hopefully you know. So KSP is the solubility product, right? And remember that these are the equilibrium constant for things that are typically insoluble. And the general way that these reactions are written, right, is Typically, we have the solid on the reactant side and our aqueous ions on the product side, which means when we write KSP expressions like something like silver chloride, it is typically just the products that are involved in our KSP expression, again, because our reactants are typically always the solid here. So usually that is what we see with KSP values. Also, because these things are typically for things that are insoluble, they're typically small numbers, really small numbers. And what that implies is, like normal for our equilibrium constant, that we mainly have reactants at equilibrium, which would make sense since we mostly consider these things to be insoluble and would stay together and form a solid. Now, there is a way that we can sort of think about, whether or not if we mix a couple of things together, would we get an actual solid to form? Would we expect a solid to form? And there are some factors involved, but in general, we could use Q again here to help us and compare Q to the KSP. And if Q is less than the KSP, we would expect no precipitate to form. And really at that point, you have sort of a unsaturated solution. If we have Q that's equal to the KSP, it typically is a saturated solution. Remember, a saturated solution is basically a solution where you've hit the maximum amount of solid that will dissolve in a solution or a solvent at that point. And if you're right at that point, if you put more solid in, it will not dissolve, basically. And that brings us really to the last one, which is a Q is greater than a KSP, which is sort of that situation. And if it is, we would expect a precipitate to form, and that's what's sometimes referred to as a supersaturated solution. Now, a reminder that Q here is the same Q as everything else that we've used it for. So if we were going to do Q for this guy up here, it would be the concentration of silver times the concentration of chloride. So again, we calculate Q the exact same way as we calculate any K, basically KSP or whatever it may be, and we can use that. Now, we also had some things that do affect, sort of the solubility and whether or not you would expect to see a solid form or not. And one thing is concentration. So depending on the concentration of the ions present, again, we can calculate Q and determine whether or not, based on those concentrations, would we expect that solid to form by comparing them. Another couple of things that have an effect on solubility and maybe something happening that we may not expect or may not expect based on, say, solubility rules. Another thing that affects solubility is that common ion as well. So we did see the sort of the common ion effect here as well with our insoluble guys. So for example, if we did have our silver chloride here, and if we did not have it, say, in water, but we had it in something like, a sodium chloride solution, this sodium chloride solution would break apart into sodium and chloride, making chloride our common ion. And basically what that would do is, again, based on Le Chatelier's principle, shift the equilibrium to the left, and again, going to cause it basically to stay together. So a reminder that if we were to calculate the solubility here of something like silver chloride, whatever the KSP value is, we'll go with 1.6 times 10 to the minus, we'll go 9. It's not right. I just made that up for sure. But basically how we would do this if we just wanted the solubility of this in water is we could do a nice table here. It would be 0, 0. And remember, these are the tables where we end up using S here instead of X. And again, what S represents is the molar solubility. And again, what we do is just go into our expression. And that would give us S times S equals the KSP. And then you could solve for S, whatever number that gets. And that number that you get in terms of S would be the molar solubility in moles per liter. And as we talked about, pretty much when you do solve for S, that is actually the solubility of the entire thing, because again, it's a 1-to-1 relationship. If it's like a 1-to-2 relationship, you know, that all sort of works the same way. We could get the grams per liter solubility by multiplying by the molar mass, right? If we multiply by the molar mass, we would end up with how many grams per liter the solubility would be in that particular case. So remember, in terms of solubility, we oftentimes talk about it in sort of two ways: moles per liter, which is the molar solubility, or grams per liter, which obviously is how many grams you could dissolve in a liter of solution is oftentimes used. So again, when we would do an ice table in a common ion type situation, the deal is here on the initial, I'll just do the initial part here. This would be 0, but we would have a number here that would come from our, say, sodium chloride. And again, since these are relatively small, you can make a pretty good assumption in certain cases and assume that S is equal to 0, and that kind of makes the calculation a little bit easier. So again, we use KSP to help us find things like solubility, molar solubility, regular solubility. We also can use the KSP value to help us decide which one would be more soluble. And you could use KSP values directly to compare, as we talked about, when the 2, 3, however many sort of substances you're comparing, they break apart into the same number of ions. So for example, here's silver chloride. You could take silver chloride and you could compare it to something like silver bromide, which also breaks apart into 2 ions. You could take the KSP values and go directly like that. If you took something like, say, calcium hydroxide, when that breaks apart, calcium plus a couple of hydroxides. Again, here, this is 3 ions, so you could not directly use the KSP values to help you determine which one should be more soluble or not. So it does have to be sort of apples to apples when you're comparing KSP values. But if they do break apart into the same number of ions, you can compare them, and it's basically the same idea as what the K value normally tells us. Again, if the K value is a large value, that means we mainly would have products at equilibrium versus something that has a smaller KSP value, which means we mainly would have reactants at equilibrium. So the guy with the larger KSP value would imply that it would be more soluble than the guy with less or a smaller value for KSP. Again, if they do not break apart into the same number of ions, you actually have to do a calculation like on the screen here and actually calculate what the solubility of each of these guys in water and then compare them. But again, if they do break apart into the same number of ions, you can sort of directly compare them using the KSP value. Another important sort of thing that we talked about in conjunction with KSP and that can affect the solubility is pH. And remember that pH in terms of insoluble acids and bases, they become soluble in basic solutions, while insoluble bases are soluble in acidic solutions. And I think maybe one of the examples we looked at was magnesium hydroxide. When it breaks apart, you get magnesium plus a couple of hydroxides here. And if you wanted to, you could use the OH concentration here if you knew the solubility, or just do the regular 00S2S and all that kind of stuff and figure out what the concentration of hydroxide would be at equilibrium. And you could get the POH from it and also get the pH from it and have sort of a baseline as to what's going on in terms of what the pH of that solution would be, say, in water. Now, if we take this, which is obviously a base, and we add acid to it, for example, when we add acid, we are going to be adding H+, and that H+ and OH- have a very high attraction for one another. And when you do that, what essentially is going to happen is the OH- here is going to be removed. And when the OH- is removed based on Le Chatelier's principle, it's going to cause the equilibrium to shift to the right. And when it shifts to the right, obviously we are going to be able to dissolve more of the magnesium hydroxide than we would, say, in the water solution. And the opposite is true if you had an acid. If you had an acidic salt, you would have H+ here on the product side. And when you would add a base to it, you would essentially be adding hydroxide. And the same effect's going to happen. These guys are going to come to make water, which is essentially removing the H+ that was there, also going to cause a shift to the right in that insoluble acid. So pH is really an important factor in terms of solubility, especially when we're dealing sort of with acids and bases, and can make them more soluble if you kind of lower the pH or raise the pH, depending on sort of what you are dealing with in that particular case. And sort of lastly, what we talked about in terms of KSP is we talked about we could use the KSP values to selectively precipitate out ions. So for example, I think that we did have one where it was silver chloride and sort of silver bromide, and an idea where if you had floating around in that solution, bromide concentration and chlorides flying around, and you could figure out exactly the sort of the concentration of silver you would need to add to actually see the silver chloride precipitate out or the silver bromide precipitate out. So for example, here, if we looked at the silver bromide, and again, the KSP would equal our silver concentration and our bromide concentration. And again, if you knew what the concentration of your bromide ion was, and I think in the example we did, it was like 0.1 molar or something of that nature, you could use this expression, really just rearrange for the silver concentration, and it would equal the KSP divided by the bromide concentration. And the number that you would get here when you actually use the correct numbers there would be the concentration of silver, sort of the minimum concentration of silver that you would need to start to see silver bromide basically start to precipitate out. And if you remember from that example, essentially silver bromide was less soluble than silver chloride. And that's because the KSP values, if you compare the KSP values, you would see that silver chloride had a higher KSP value, which means it would be more soluble. And the reason why you would want to sort of maintain control of something like this is exactly what we sort of do with qualitative analysis. And you could do a similar calculation using the silver chloride KSP and get the silver concentration needed to see the silver chloride precipitate out. And you can really selectively precipitate out one versus the other here by keeping the concentration high enough in this particular example to precipitate out the bromide as silver bromide while leaving the chloride floating around the solution. And you can continuously raise the silver concentration like we talked about until it gets to just below the concentration needed for silver chloride to come out. And at that point, you hopefully will stop seeing some solid form, and then you could raise it to the minimum concentration of silver needed for the silver chloride to come out, and you again should start to see solid form. And again, this is a way you can selectively precipitate it. If you're not really thinking about it, you just dump in a certain concentration of silver in there, and it's maybe too large of a concentration. What would happen is both of these guys would, as we talked about, sort of co-precipitate out together, which in certain cases is not a good thing, because in this case, they are each basically a white solid. So it would be no way for you to go, I think this white solid is silver chloride, I think this one is the silver bromide. So again, there would be kind of no way to distinguish them. So again, if you kind of selectively precipitate these guys out, you're able to really sort of isolate and zoom in on the idea of which one's coming out and have a pretty good idea which one's coming out first. Now, the sort of last topic here in 16 we came back for, which is Kf, and that's the formation constant for complex ions. Maybe I should stop right here. I don't know. All right, we'll finish up 16. All right, free review for 16 here. So formation constants, these are the Kfs. They're basically for complex ion formation. So for example, silver plus, you know, some ammonia here. Forms this complex ion. And when we do these problems, usually the Kf is, again, just like normal, our products over our reactants. And basically, when we do this, the Kf values, as we talked about, are very large values. And because they're large values, even though it is a reversible reaction, we do make a couple assumptions when we do these problems. We assume that first off, everybody's heading in the forward direction here, even though it's a reversible reaction. Essentially, all of it is going to go this way. And because there's such a high value for that Kf, it does want to make that complex ion, which the first assumption we assume is that all of the metal gets used up. So when we do this ice table, the change part should be the metal that's there. And basically what that will mean is we will kind of zero out the metal. And if you remember that once we zero out the metal, we do have to realize that it is a reversible type reaction, which means even though we zeroed out the metal, there is going to be some of this guy heading back this way. And the second part of that assumption is the amount of free metal that should be there should be very, very small. And we can then use our Kf expression and solve for the metal, which is usually down here. Because we will have the ligands concentration, and we'll also have the complex ions concentration as well. So usually at this point, after you do the ice table, you have this concentration, this, and this. It allows you to go back and solve for the metals concentration, which again should be a relatively small number to sort of justify our assumption that we made. Remember that the ligands here do come on one at a time. So, you know, the first step is, for example, the first one gets put on here. And you can't have a K value for that. Next one gets put on. And also could have a K value for that and so forth. And you can have that sort of stepwise formation that occurs of this complex ion. And remember that if you add them all together, you need to multiply the K values together, and you could get it from, use the overall K value there for that reaction. All right. So I think that is chapter 16, and we will stop there today to take a little break before we start our exam at 3. Couple of reminders, exam will be at 3 like normal. You do need to have your camera. Again, a reminder that I need to kind of see your work area and also you a little bit to make sure it's you, not just fingers coming in to the screen. So not a super wide shot, but wide enough that I could, again, see your work area and kind of recognize that it is you taking it and all that good stuff. Any questions on anything before we go? All right, so we'll start around 3. Make sure you're logged into the Zoom just like normal. You cannot leave your area, right, or anything like that. So take care of all that stuff that you need to take care of, restroom and all that. You're not allowed to leave sort of the camera view for any reason. At the beginning, like normal, you could go print it, and then when you're done, just let me know you're done, and then you could go obviously upload it and all that good stuff after you're done with the exam. Obviously no phone or anything like that out until that part of the exam obviously is done. All right, I'll see everybody about 3.